All right, let's get started. So today we're going to talk about this slightly different style of paper, and the context is really trying to discuss the connection between formal methods, or formal proofs to be more precise, and security, and what they have to do with one another. This is a slightly weird paper in some sense because, as you've probably realized reading it, these guys don't really develop a new thing or really have something technical, concrete to say in one sense of the word. But these guys are experts, right? So actually, I guess we didn't say who these guys were, but the first author, Toby Murray, is one of the developers of SEL4, which is a really significant result that came out a little more than a decade ago now, where these guys verified a very realistic low-level implementation of a microkernel, provides strong guarantees. And they have a string of papers, highly influential work. So this guy really knows what he's talking about in terms of writing security theorems and specs and so on. And the other guy is a security expert. So these guys understand sort of security, formal methods, verification pretty well. So it's interesting what they have to say. In some ways, this is more of maybe a discussion paper or philosophical discussion of what's going on, as opposed to some technical idea that we've seen in previous papers. So one thing I wanted to mention, like actually, it's a bit hard to figure out what should we take away from this paper. It's a lot of interesting discussion. For me, the way I sort of internalize these results is really sort of, you can think of under the heading of, what should you expect if you're doing proofs? So the sort of hypothetical question is, you're building some important system, you want security, and you're thinking, well, proofs might help me. This paper might actually be a sensible thing to read and think about, because it provides some tempered expectations, like what should you expect to be the outcome of proofs? How do you set things up so that you get the outcome you want? And so that you don't give up security in some other way because you did a proof. So it's really sort of this, setting the context right. If you're thinking of using proofs, this paper might orient you or help you understand why doing proofs would be useful for you or not. So that's, I think, the context. Partly this is because this is a discussion paper. Feel free to jump in with questions anytime. I guess it's always true in our lectures, but especially so here, I think easy to have lots of opinions about this, and feel free to jump in and ask what you're thinking about. So one level down, sort of separately from how to internalize what this paper is saying, why this paper seems important is that, in fact, security is a good motivation for verification. As we've seen, there's hard problems in security that have to do with getting everything right, and verification, at least at an intuitive level, seems to be a good fit for that kind of a domain where you have to make sure you got all the details correct, and formal proofs can sort of help you there. And what this paper is really looking at is sort of how do proofs actually influence security. And there's sort of many things that you could imagine maybe going wrong or not being quite lined up. These guys talk about various gaps in terms of formalisms. You thought you proved a theorem, and it is a true mathematical theorem, but what does it have to do with reality in various ways? Maybe you misformalized the underlying platforms. Maybe your theorem doesn't say what you thought it would say. And in general, I think one message from this paper is that it's really difficult to model reality correctly. And if you're living in a existing world, running on top of existing processors, or even building on top of transistors, it's going to be really hard for you to come up with a precise model of how this real world operates. So almost inevitably, your theorem statement is going to be not exactly applicable to the real world if you look very nitpicky at all the details and try to pin everything down. So the question is, what is the value of a proof if, logically speaking, it doesn't quite apply to the real world? So that's one aspect this paper struggles with. The other is really some potentially side effects of doing a proof. Is that actually maybe, is doing a proof always good for you, or are you giving up something? It's like an interesting discussion. And one thing too, of course, you probably have noticed is that a fair bit of overlap with some of the prior papers that we've seen in this class. And of course, the most closely related is the paper that we read, I think 2 or 3 weeks ago, about the empirical study of distributed systems, where those guys looked at some verified systems and tried to see if there's bugs. And those guys sort of, point out in the empirical study paper, they point out some issues where things didn't quite work out so well, where there were bugs. This paper is sort of trying to, I think, look more holistically. What is the value end to end? And also, you probably remember the Amazon paper that we read very early in this class. And those guys, in some sense, are getting value without doing full proofs. And it's interesting to sort of see what's going on with these Amazon guys. How are they extracting the value out of not quite full proofs, and why might you want to do a full proof instead? So that's the sort of setup for this paper. I figured we'll discuss various aspects of it, sort of maybe in different ways, and we'll see what we come up with. But again, jump in with questions if something seems interesting or unclear. So one thing I wanted to start with is to maybe reiterate in some ways, what's the value? Why would you want to do proofs for security? And then we'll talk about the opposite question of like, why would you not want to do proofs for security maybe? So just to make sure we're on the same page, the reason why you might intuitively really want to do proofs for security is that, as you might remember from Butler's lecture, security is this kind of a negative goal. And what I mean by negative goal is that security says that, like, regardless of what the bad guy does, there's no way to compromise the system. And this is sort of at a root, like, the real reason why security is so difficult, because it's not just that your system has to work and like, well, if it doesn't work, try rebooting it, like the usual sort of advice for computer systems. Instead, it has to be the case that, like, no matter what you do, you reboot it, you poke it in the right way, it always is secure. And that's really tricky. And this is, I think, intuitively why many researchers feel like formal verification is a great fit for this problem, because in this problem domain of security, all these corner cases actually matter a lot. And in a sense, these corner cases for security, like bugs in some obscure condition where the user sent this message and the system was in exactly this state, these kinds of crazy corner cases, we sort of argued that they're also important in other domains, like concurrent software, distributed systems. All kinds of strange things could happen because computers fail or you have many threads. In some ways, these corner cases matter a lot more in security, because in concurrency and distributed systems, there's some kind of an environmental thing going on where your threads are sort of running along. It's not like they're adversarially out to get you. And distributed systems, they do crash, but it's unlikely that 5 computers will crash at exactly the same millisecond or in some sequence to like spite your algorithm. That's not going to happen with very high probability. So there's a stochastic sense in which concurrent and distributed systems are perhaps better behaved. And adversarial systems or cases where you worry about security can't really think the same heuristic or stochastic way about their behavior, because the adversary will carefully line up the attack and make very unlikely events happen.
So it's an interesting question, how one should look at last week's Amazon Web Services outage in the light of these observations.
Yeah, so I think with as systems get larger and there's more of them, more unlikely events do happen. So
because in a way it was an example of things getting lined up.
Exactly, yeah. So maybe what more precisely the way for what I should have said is that if we had attackers, we would probably be seeing even more crazy coincidences that cause failures at large scales. So indeed, large systems fail in some subtle ways and 5 things do line up, but a bad guy can make 20 or 100 things line up. I think just in some ways it's a question of degree, perhaps. Important to handle rare cases for distributed systems, but I imagine that Amazon wouldn't be nearly as reliable if adversaries could control the timing of their systems. Maybe that's
No, I'm sure that's true, but actually I was thinking along somewhat different lines that this outage and a number of other ones that clouds have had over the last decade or so illustrates that it's surprisingly easy to design your system in such a way that unfavorable things tend to line up.
Interesting, yeah.
And so you need to think about that all the time, even in the absence of adversaries.
Right.
How can an overload condition feed on itself in such a way as to make itself worse?
Yeah, overload, I guess, is indeed a classic example of bad feedback, and often sort of shared across systems, especially on a cloud setting like Amazon. Yeah.
Which is exactly what happened last week, apparently.
Yeah.
And it was quite funny. The resource that they ran out of was threads that the operating system was willing to construct.
Right. So slightly artificial. So in some sense, or some kind of a descriptor, I forget the detail, but easy to imagine. Retrospectively, of course, easy to say, well, they should have been monitoring this resource, not resource, but hard to predict everything you got to monitor. Yeah.
Anyway, sorry to distract you.
Oh, no,
observation.
Good point. All right. So indeed, so corner cases matter here. And of course, sort of proofs are good at, consider all cases. So that's a useful property of proofs that is at the heart of why security might benefit from formal methods. And more so than just considering all cases, machine checked proofs are great because there's no human that'll make a mistake and gloss over any detail of a proof. And the sort of pinnacle of this line of thinking is that, look, the code is irrelevant. Just look at the spec. You just need to consider the spec, and that should tell you everything you need to know. Sort of the extreme line of thinking in this direction, but that's the hope. And if the spec is sort of concise and captures everything you care about, great. We just need to worry about the spec. And that's, I think, the story that we've been trying, sort of, explaining all along as what proofs provide. And this paper sort of, realizes this. These guys, of course, are experts in verification as well. But they talk quite a bit about why this might not line up with reality, as I was saying earlier on. So does this make sense? Any questions so far before we jump into the sort of all the details or all the reasons why these guys say the proofs might not be as great as they are? All right. So let's talk about, I guess, the opposite. So, why not maybe proofs for security? So one way I was thinking of maybe we could do this is, what are you guys sort of most interesting examples from this paper that you guys thought were compelling for why might proofs not actually work out super well for proving security? Anyone want to jump in? Maybe I'll pick on someone, maybe Caleb. If you're around. Perhaps not.
Caleb's audio typically doesn't seem to work.
Oh, that's right. Yeah, thanks, man. Yeah. Thanks for reminding me. Yeah, sorry about that. Well, sorry for picking you now. If you jumped in, Alex, do you have what is your favorite example from this paper? Why they think proofs aren't a panacea?
I mean, this isn't directly from the paper, but the paper and the question obviously made me think a lot about the labs. With in terms of, I had an implementation that was just very not easy to prove for lab 3A, I think was correct. And this just made me think a lot about how I had to change the implementation to make it easier to prove. And I think that I guess there were examples of that in the paper as well, but that just like it really hit home because like I had to do that.
Yeah, sorry, yeah, I think that's a great point. And like in some ways, I think the paper, they have some weird examples, partly motivated by like the exact things they saw in developing SEL4 and some other systems that they cite. But I think the broader point you raise is indeed quite important. And maybe let me characterize it in two ways. So one, I think thing going on is that there's lots of effort going on to prove a system, to sort of make the proof go through, as you guys are all extremely aware of now. And the question is, what are the alternatives? And it might be the case that there's some better things you might do in life, or in this context, like to build a more reliable system. Like there's probably things you could do, like fuzzing, or maybe you could do audits, or maybe you could, refactor your code, or maybe provide better isolation in your code, split it up into smaller pieces that are isolated from one another. All kinds of good stuff for security. And that's one way to think of it. You spend a bunch of time proving, was it actually worthwhile? Should you have instead just like look at your code and thought some, or fuzzed it, or done something else? So maybe that's one way to sort of interpret what you said, or one part of it, which is like a lot of effort to do this. The other thing going on is that actually there's lots of, idiosyncratic code. So in order to prove things like lab 3, as you were saying, you got to write your code in a very specialized way to make the proof go through. And, it's a particular style. And as you guys have probably seen, like it's not the most natural thing necessarily. If I was not writing this code to be verified, probably wouldn't write it in Coq or Haskell or Camel to begin with. I probably wouldn't have write functional code to begin with. Maybe I would write it in Go or C. Like C maybe is a bad example for correctness, but writing it in a language like Go or Rust perhaps is a sensible plan. So there's certainly some tension that we are seeing, and that this paper tries to get at in terms of how you would design your system and write the code, implement it for verification versus other desirable things. And I guess there's some things going on. One is like maybe the code is less clean, so it's harder to maintain. The more damaging thing might be, the paper sort of indirectly alludes to this, but maybe the code is error prone in ways that aren't about the spec. Sort of bypass the spec. What I mean by this is that the spec only covers some part of the system behavior. Maybe you don't actually describe exactly how fast it is, what the performance is, when does it, all kinds of, properties about, not crashing, not taking too long, who knows? Lots of like theorems are very precise as what they demand in terms of what they demand. And there's many other things you might want from your code. And maybe writing code to prove a very specific theorem means that your code is not as good in other dimensions. So that'll be also kind of damaging. So that's certainly some downsides of proofs. These are in some ways very concrete downsides almost of proofs. We're talking about, well, like you should have done something else and been more effective, or you like wrote worse code as a result. There's also a bunch of things going on in the paper about the fact that proofs might just like not give you as much as you were hoping. So in some ways, like it's really important to have a threat model for security. So if you recall from Butler's lecture, if you want to think about security, you got to understand what is your adversary capable of doing. And it's important to enumerate this stuff because some kinds of adversaries you just can't defend against. Like if your adversary is Intel supplying you a bad processor implementation, it's like going to be hard for you to make much progress. And if you assume sort of every silicon vendor is out to get you, it's going to be tough. Same as like if your users pick bad passwords and lose their phones all the time, also hard to make progress. So you got to assume something about what the adversary can or cannot do. And one interpretation of formal methods is that it forces you to really write down a precise threat model in order to write down your theorem statement. But I think what this paper is really saying is like, well, the kind of threat model you get out of a formal proof exercise is like an extremely pedantic model or pedantic threat model, and it's actually incorrect. In the sense that, well, first you have to be extremely pedantic to pin down all the details of like your underlying, CPU or whatever thing you run on, pin down exactly what spec you're trying to provide. And then partly because you were so precise about pinning all these details down, you probably got them wrong in some subtle way. And maybe it's not a way that really matters in some grand scheme of things. Like your system might still be okay or pretty correct or pretty secure. But as far as sort of formal logic goes, your threat model was wrong because you made a small mistake. And now the theorem just doesn't apply in the real world. So that's, I think, a broad characterization of many of the complaints these guys have, or nuances these guys articulate about applying formal methods directly for security. And maybe I'll try to sort of, try to maybe cluster these nuances in maybe sort of three categories. One thing going on is certainly you made the wrong assumptions. And the paper, because it's coming from the SEL4 developers, these guys wrote a microkernel, so they worry a lot about the underlying processor details. So a common thing that they sort of point out is that it's easy to have an imprecise CPU model. So they give examples of, model the ARM ISA. People have modeled the ARM ISA several times. A number of these models are actually really good and quite accurate. But it might be the case that the model was really intended for a different use case. So one easy example to point out is like maybe your model of the CPU is missing information about any timing of instructions. It's just about what inputs you give to an instruction and what outputs you can expect when the instruction completes. And timing might be important if you're trying to prove a property about non-interference that involves adversary trying to measure the time, how long various operations take. This might be the case, for example, for these speculative execution, aspects of CPUs that people have gotten excited about recently. Another thing that might be missing from your model is non-determinism. So the authors of this paper point out several, actually maybe one example where it's like a very well designed model of the ARM instruction set, and it sort of over constrains the spec in a way that the ARM book does not. So the ARM book that like the ARM organization publishes says that certain instructions have, unspecified or, behavior that's not exactly pinned down. For functional correctness, maybe it suffices to say that, well, just like don't ever call that instruction in that way. That's undefined behavior, and prove that your code never touches this bad behavior of execution. But it might not be good enough for non-interference if that's what you're trying to prove. So maybe there's some aspect of the CPU that you forgot to model. Another thing is missing features. And one way to think of this is that it's very tempting to say, well, we're going to verify a small system. We're not even going to use all kinds of crazy aspects of the CPU. Like I'm writing an operating system kernel. I don't need to worry about floating point because the kernel doesn't do floating point operations. So could I formalize a version of the hardware instruction set that omits the floating point stuff? And in some ways, this is doable. So for example, like the Certicos guys go down this route, and several actually other projects do the same thing, where they formalize a subset of the instruction set architecture. And then as long as their code only touches that subset, they're actually pretty good for functional correctness. But it's not so good if you want to reason about arbitrary user level code, because the arbitrary user level code could invoke those funny instructions you didn't model, and maybe it does something that you didn't realize was going to happen. So they mentioned one example of the SEL4 kernel where they forgot or didn't model one particular register for supervisor execution. And someone discovered that, yeah, well, in reality, there's this extra register and it could, in principle, leak information. So maybe one lesson is that it's there's really subtle expectations about what a model is good for, as we see here for non-interference, for maybe confidentiality, for timing, for various things. And it's like easy to make a mistake not even intending to use a bad CPU model. All right, so that's one category of how maybe your threat model is wrong, or the execution model is wrong. The other is really sort of related to this negative goal I stated about security in general, is that, attackers try to, bypass known defenses. So it's probably the case that if you can prove some property of your code, probably that property holds. Like if you have a very well designed, OS kernel that in principle, like correctly handles every system call, that's probably true. And the attackers are going to look elsewhere outside of your precise threat model. And there's sort of many examples of this. Maybe one very sort of top level example is that no matter how good your OS kernel is, probably phishing attacks are still going to be a big deal for your system. So important not to lose sight of the big picture. But then there are sort of other aspects that you might not have thought to include in your theorem statement. So one example is various kinds of side channels, sort of having to do with timing attacks. Maybe one way to sort of contrast this side channel thing with this timing information up here is that here, what I meant to say is that the assumptions underneath of your proof are wrong. And here, I'm talking about another class of problems where your theorem statement doesn't quite capture everything that the attacker might do, or the theorem statement doesn't cover some bad behavior the attacker can cause. So they could measure timing, and if your theorem forgets that, that's unfortunate. Another actually really common way attackers bypass all kinds of stuff is through various, debug or management mechanisms. So what I mean by this is that in most systems, there's a way to debug the system, or even in hardware, there's a way to debug the hardware. There's JTAG interfaces. There's all kinds of management software running underneath of even sort of a processor in some sense. So for example, all x86 machines have a lot of complicated code running in a thing called system management mode. Typically, it's not part of your execution model when you're trying to do a formal proof of correctness, but there's probably bugs in software in that system management code. And the attacker can probably go find bugs there and subvert your whole execution stack. So there's that. There's probably other physical effects. Physical attacks. Maybe I should have included sort of physical attacks even up here. So what I mean by physical attacks are sort of two kinds of things. One is that it might be that the bad guy has physical access to your device. If you're building something like an Xbox or a PlayStation, these guys worry a lot about the person holding the PlayStation in their hands, trying to tamper with the processor and do something with contents of games or execution state in that machine. So that sort of falls into, well, you better have included that in your theorem statement somehow. Another kind of physical attacks are things that Butler mentioned in his talk, things like, for example, row hammer. This is a class of attacks that take advantage of physical effects and DRAM chips to flip bits of memory. And typically, when you model memory as having perfect, correctness. If you store a value there, you'll get it back unless you modify it. But in reality, some DRAM chips have some physical effects going on that cause values of memory locations to flip randomly, or maybe not so randomly, depending on how the attacker arranges neighboring accesses. And that really is undermines your whole model. You're just wrong about how to think of what the attacker is capable of. So important to sort of keep in mind both the sort of execution model and what you're capturing in your theorem statement. Tricky to know when this is all lining up correctly or not. Maybe the last sort of category, sort of related to the theorem statement, is sometimes actually really hard to interpret. The theorem that you've proven about a system. And we've talked about this in several lectures already, about the importance of having a very concise spec that captures what you want. And to the extent possible, like if you can prove another application on top of the spec, you'd be in business. But oftentimes these are sort of proof systems like a microkernel that aren't an application. They provide a platform of their own for running applications on top of. And one sort of maybe slightly depressing anecdote they give in the paper is that this researcher, Benjamin Pierce from UPenn, he's an expert. He actually wrote or was the primary author of the software foundations exercises you guys did at the beginning of this class. He really knows his stuff in formal methods, but for him, it actually took like a solid week of effort to basically read the SEL4 theorem. So these guys have a theorem that says what is correctness of SEL4. This guy spent a week of his life trying to understand that theorem statement, not the proof, just the theorem statement. What does that mean? This is like a really, in some ways, depressing statement that, this really expert researcher needed to spend that much time to understand the details of this theorem. What could anyone else expect to do? So tricky stuff. And so this is what sort of the cautionary tale in some sense this paper puts forward, that these formal methods aren't providing exactly the sort of ironclad guarantees that you might informally expect these proofs to be providing. Make sense? Any questions or comments on this way of thinking? All right. So the other way that I wanted to maybe talk about what this paper is arguing about is the way the paper presents it sort of argues about code changes. So in some ways, this is maybe a more concrete way to visualize what we're talking about, of sort of all these assumptions and so on. So the paper has this whole series of Venn diagrams. But for me, I actually found it useful to think of it in slightly different terms. So the Venn diagrams they show are like all kinds of various overlaps and this and that. But I think it's actually all stemming from the same basic picture. They're thinking, what are all the changes you could make to your system to make it secure, to verify it, etc. And then sort of categorize these changes. Some changes you need to verify the system. And you might have some changes that are needed to verify the system. Yes, you need this change to make the proof go through. This is the P category that they show. And some other changes you might make that are just like not relevant to verification. You can make them, that's fine, but you could verify it anyway. And then there's another dimension that they worry about is that, what kinds of changes do you need to make the system secure? And, some changes you might make that are irrelevant to security, and then some changes you might make that are relevant to security. This is the A set that they have. And then they basically, all these Venn diagrams are talking about how big each of these four squares is in relation to others and what the overlaps are in some sense. So one way to look at this is that things in this quadrant, they're changes that are not relevant to verification. They're not relevant to security. Well, this is just like some mundane stuff that you could change that's not really about the security or verification at all. Fine. The other sort of maybe opposite category is like, these are changes that you need to verify stuff and they're important to get the security right. This is just like great. This is why we were trying to do proofs to begin with. This change, you have to make this change to make it secure. And look, you wouldn't have been able to make the proof go through unless you made the change. That is cool. And then there's these other sort of places here and here. I think the authors basically think of this quadrant as sort of like overhead of proofs. This is a change that you had to make in order to make the proof go through. This is sort of the changes that maybe Alex was alluding to a little while ago. In your labs, you're probably monkeying with your code and trying to change in all kinds of ways to make the proof go through or make the proof easier, even though it probably didn't really make a difference for correctness. It's just about simplifying the proofs. So this is this category these guys are talking about. And then there's this other category, which is kind of a weird category. Maybe one way I can characterize it is that, maybe this is a case of a misguided theorem or an incomplete theorem. Basically, these are changes that you really need to make your system secure. But the proof didn't force those changes to happen. So you could easily be missing these changes in a verified system. That would be unfortunate. And they might be missing because of all the reasons we talked about on the previous slide, like your model of reality might be not quite right. Maybe your theorem statement is too weak. Who knows? So this is really what these guys are trying to articulate with these diagrams. And the diagram they show in the paper are basically all of this shape where they have the P set over here and the A set. And then they sort of say, well, okay, this is the overhead. This is this shading. Then the overlap in the middle, this stuff is the great stuff. And then there's other changes like here in the A category. Well, these are the actual attacks that would be great if you stopped, but maybe if they're not in the P category, they're here. So that's all their Venn diagrams, I think, are doing. And they sort of shift these circles around to argue, oh, you know, this section might be big, this section might be big, this section might be big, etc. Another sort of, the only other interesting point they make in the paper about these Venn diagrams is a particularly worrisome set that they hypothesize might exist, which is the V set. So they sort of draw it here. It's like a subset of some changes you made in the overhead category. And what this V set is like basically, you know, or, you know, broke security. This is the V set. So the V changes that they're talking about are things that you made to make the proof go through, but it turns out it broke your security in some other way. So one way to think of it is like maybe your theorem statement was provable by introducing some change to your login process or to your your UI, and that was like fine by the theorem statement, but it made your system much more susceptible to phishing. That's an example of, I think, a change in this V category, perhaps. That would be really unfortunate if you had to weaken your system in various ways in order to make the proof go through. So we'll talk about other ways in which maybe this V category shows up. But one thing I wanted to maybe do now is give you guys a little bit of time to discuss the reading question we assigned for this paper in breakout groups. So just to remind you, so the breakout question was, you know, what's your experience with verification, and maybe concretely in the labs or other projects you might have been involved in, and what has your experience been? Where are the changes you're making? Are you actually fixing bugs that you initially had? Like, do you have big stuff in this great category, or are you making a lot of changes to the code that are sort of irrelevant to the real security or correctness? They're just there to make the proof happy. Or did you actually find cases where you made a change and it turns out it like broke something unfortunate or would have broken something in a way that the theorem didn't even capture? So that's the breakout question. Any questions before we sort of jump into breakout rooms to give you guys a chance to talk about this stuff? All right, so I'll put you guys in breakout rooms now, and see you guys in 10 minutes, give or take. All right, so it seems like everyone's back now. So maybe I'll pick a couple of people from different groups and see what you guys thought. So maybe from the first group, I already called on Alex before, so maybe I'll ask Eileen. So what did you guys come up with? What was your experience like?
Yeah, we talked about a few different things, like in terms of changing the code in the labs. There's some stuff that we did to make stuff more easier to prove. I think Alex mentioned like where you were storing the size of the log in the like at the end or the beginning for the log lab. Caleb said like, oh, there's one-off errors that kind of you just wait for the proof to pick it up. And I think in terms of like our actual code, we're talking about the trade-off between like correctness and what looks weird sometimes, because there's some stuff that's like very intuitive and like this makes sense when you look at it, but then it actually isn't correct. So that was some of the interesting stuff that came up.
Yeah, good point. Yeah. So certainly, you know, okay, so it sounds like at least there's some cases where you had like real-ish bugs here. One thing you mentioned that's actually resonates a bit with our experience doing verification in our research group is like when you're doing verification, there's a little bit of a tendency you get to just like, if there's a hard thing, like a off by one error, just like, I don't know, write some code and, you know, the proof will catch it, as you say. So I think we certainly noticed that like, I personally, like when I was writing code for FSCQ, sometimes I didn't know if it was +1, -1, or +0. I just, you know, pick something, and then the proof would indeed catch it. So sometimes it actually works really well, like off by one errors typically line up nicely for that. And there the proof really helps, although it's kind of an artificial bug in the real category. If you were writing real code, you probably wouldn't have been so sloppy. But yeah, so a fair point. And I think sort of the last thing you mentioned is sort of really sort of funny looking, or code that you would write to make the proof go through. So I think that's a real thing. Like, well, I guess first of all, you probably wouldn't write your implementation in Coq to begin with. But there's probably many properties like memory use. Like if you're writing a disk remapping system or something else, or replicated disk system like for Lab 4, you would probably worry a bit about how much memory you're using and like how fast each operation is. That's like totally not covered by the theorem that you guys have in the lab assignment. So it's easy to write code that allocates a whole bunch of blocks for who knows what reason. And this might actually cause your disk remapping system to run out of memory and exit or stop running. And the theorem actually says that's fine. The theorem in Hoare logic is a partial correctness theorem that says if you return, then better be the right result. But it's always fine to spin forever or never return or sort of run out of memory. So there are situations that certainly you could write funny code. One of the actually interesting things, one of the authors of this paper, Toby Murray, so these guys worked on the SEL4 kernel, and one interesting thing there is that they really didn't cut almost any corners, or many fewer corners were cut in terms of the realism of the actual microkernel implementation. So one thing going on is that they really insisted on satisfying very close to the regular microkernel L4 specification, same API. So that really forced them to be pretty precise and faithful in what they're verifying. The other thing is they actually had sort of two teams, as sort of an aside comment, but they really had sort of two teams. One team responsible for writing the microkernel code. These guys were kernel hackers, and another team was responsible for doing the verification. And as a result, there was a bit more, I think, of an activation energy required to make some, mundane change to the kernel implementation to make the proof easier. So it presumably still happened in some ways if there was a big benefit, but many fewer, I think, small changes would happen in the microkernel implementation than if you had the same guy doing the proof and the verification and the code implementation. So by contrast, like in our research, like our research group, we often have the same people, of course, writing the code implementation and the proof at the same time. And we just flip back and forth all the time. If there's like even a tiny bit of annoyance at the proof level, we're just like, whatever, let's change the code, no problem. And it sort of has some of these effects I think you mentioned as well. You end up with funny looking code.
So Nikolai, I think actually where this came up was more extreme examples of like basically synthesized code.
Oh yeah,
where
that
you get to an extreme where the code is almost unreadable, or it's pretty printed by a printer that is not very pretty, and so the code is just completely nonsensical. And this is kind of an interesting case where like people don't like this. The F-star team goes to great lengths to make sure that the generated C code is readable, like nicely indented, good variable names, like good style, despite this technically not mattering.
Yeah, so maybe like one example of this like V thing is actually like unreadable code. Not quite V in the sense that it makes security problems, but I think the same anecdote I think you're describing with the F-star team, I was sort of looking at it more from a perspective of the Firefox developers, where I think the F-star guys, this is the Everest project that we read earlier in this class, where these guys are building a verified TLS stack or HTTPS stack even. And as part of it, they have verified crypto implementations. And they were talking to the Firefox developers, trying to help the Firefox developers include this verified crypto code. And I think one of the big requirements from the Firefox developers was that they wanted the code to be following the same style and readability and guidelines as any other code in their code base. So they didn't really want to rely on formal methods and the proof to ensure correctness. They wanted the C code or C++ code to be perfectly reasonable C++ code on its own right, so they could go and change it if need be, if verification becomes a pain later or who knows what. So I think that was certainly, I don't know if the F-Star guys already had their code being so nicely printed, or they sort of did it in
Yeah,
response to the
I think it
Firefox
was part of
guys.
this effort. I think it was part of this push that they were pushed to make sure that the output always looked good.
Right. Yeah, so maybe one lesson to learn from this, maybe in a positive light, is like what to expect from verification is that, you probably should worry not just about verifying your code, but making sure this code fits into the grand scheme of things. Like if you're submitting verified code to the Linux kernel, can't be just like code with no indentation and variable names starting from 0 and going up. So. All right, so thanks for that. Maybe I'll pick someone from the other group. Julian, did you guys have other things that you talked about that seemed interesting, or similar subset of issues?
Mostly similar. We were also talking about the logging lab and some of the changes we had to make there that covered bugs, so that was good. We were also talking a little bit about the fact that all the labs are implementations in Coq, and so there could definitely just by doing that and not writing it in a language that you can have a lot of problems there if you don't really understand exactly how Coq works with its implementations. And then we were talking about some other things, how there's it's kind of hard, like the P and A descriptions they have in the paper. It's kind of hard to identify what's the things that are in A but not P, just because you don't know how, like, we don't know what can attack us if we're not thinking about it. But just the fact that we had that reading example a couple weeks ago of a way we could have attacked our OneDisk API makes us think that if you spend some time thinking about attacking our implementations in our labs, there's got to be some ways that our proofs just don't handle properly.
Yeah, good point. So actually, maybe just to give a concrete example of like, okay, so the question is, what is here? Like, what is a real attack that wouldn't happen, or the proof says there are no attacks, but there is a real attack. So I think like a superficial or high level, like phishing is probably like getting an email asking you to like, please type your password in here. Probably get these pretty frequently. Like that's an attack that probably is outside of most security theorems about systems. Well, it's kind of a high level. Maybe a very concrete example of something in this A category is forgetting to model some aspect of the hardware. So for instance, you forget that there's extra floating point instructions in your hardware, and you prove everything as if there is no floating point because you're writing an OS kernel. And it turns out that there's funny things going on with floating point instructions, and your applications running on top of your verified kernel can use these floating point instructions to leak data from one another. So it's easy to have sort of these question mark bugs in the A category if your model isn't quite right. And it might be right in sort of egregious ways like this floating point thing, or it might be not quite right in ways that you just like didn't even think about. So one example is these row hammer attacks. So in row hammer attacks, just to spell this out a little bit, what's going on is that you have your model of memory, you have all the values stored here, and it might be that there's like some really important value stored here that has to be, I don't know, 5, or maybe it's a pointer to somewhere that has to be exactly correct. Maybe it's your privilege level, who knows what. Or maybe it's like the bound of some array that you're allowed to access. And what happens in row, or like in a classical sort of model of memory, if you wrote 5 there, you will read 5 back, unless you wrote something else. Very natural to write that kind of a spec for memory and rely on it. But it turns out that if you buy sort of cheap memory, or even not necessarily cheap memory, but many memory vendors, in order to save cost and improve performance and power consumption, they make these chips that are implementing the memory very small, sort of shrink the features. And one side effect of that is that in some configurations, what can happen is if you store 5 there, but then do lots of reads on adjacent memory locations, lots of read operations, it somehow is going to degrade the physical charge stored in capacitors in silicon representing this value 5. So if you issue lots of reads on adjacent memory locations, that could cause the 5 to flip to something else. Like maybe that'll cause the 5 to randomly flip to a 4. That's really damaging if you pick the right value to flip. And I'm oversimplifying things in quite a number of ways here in this picture. Oh yeah, my drawing program crashed again. So despite this sort of oversimplified picture of what rowhammer does, I think it's an example of a bug that falls in this category of being in A and not in P, because it's a real bug. People do take advantage of it or demonstrated the ability to attack systems, to escape. System could have been totally proven correct, just like you got the wrong threat model. You should have assumed your memory was buggy. And there's other sort of examples in this vein, but typically they sort of fall in these two categories that we talked about before. Either you got your sort of underlying assumptions wrong, or your sort of spec was wrong or incomplete. So I think that's the reason why you might have a security problem in that A set that's not in P, roughly speaking. Hopefully makes some sense. All right, so thanks very much for that feedback from the breakout groups. Sounds interesting. So now I wanted to, we can sort of basically discuss the same set of issues that you talk about in maybe a slightly different way. What I wanted to sort of now pitch is their sort of way of thinking of why are proofs useful, even though there's all these problems about the theorem not necessarily applying to the real world. And they sort of put forward like 2.5 reasons why you might think proofs are useful despite their limitations. The first pitch they sort of call this qualified guarantees story. And this is sort of a way of looking at the proof and saying, well, what you should expect from a proof is not that it's like perfectly going to apply to the real world, but it's really just a statement that says you're secure under these precise assumptions. And there's sort of two cool things going on here. One is that it really does force you to state a precise threat model. And this is the sort of nitpicky and probably wrong threat model that we talked about before, but there is probably nonetheless value in stating this precisely. And then what you get from doing a proof is this conditional guarantee. Correctness or security that basically says your system is secure or correct modulo this exact set of assumptions. And I think this is certainly an easy view to sort of buy into. I think this is mathematically what a proof says. Like, given these assumptions, here's an outcome that we've proven to be correct mathematically. But just to sort of put this in context, the reason why none of these answers for what's the value of a partial proof are going to be fully satisfying. So there's sort of nuances to both. So if you're thinking of it in this qualified guarantee view of the world, one thing that might be difficult is that it might be sort of hard to understand the assumptions. So maybe to think of this in a positive way, if you're thinking of proving a system correct, and you're thinking, well, that'll be cool, it'll give me a qualified guarantee, then maybe you should work hard to make sure that these guarantee, the qualifications, the assumptions are very easily extractable out of your proof. Because it might be the case that in fact, you've proven some system correct and there's a whole bunch of assumptions lying somewhere at the bottom of your system. And it's really hard to figure out what they all mean or what's going on or what these assumptions even are. Maybe depends on how you set things up. So it's important to sort of keep this in mind if you're going for this qualified guarantee view of the world. Another thing is that sort of part of this extracting assumptions is that it might actually be hard to understand the implications. So I mentioned this example earlier as well, but I want to come back to it because I think it's a good example of what it means to have implications of this assumption. So the example that I described before was in the SEL4 proof. They have an ARM, a model of the ARM ISA, and they actually borrowed the model, as far as I understand, from actually, this is not an SEL4 proof. This is someone else's proof of an isolation mechanism on top of ARM. They used someone else's model of the ARM ISA, and it was oversimplified in a, well, I don't know, maybe not over, but simplified in a way that basically said there's these things called undefined or unspecified behavior. And the spec didn't really say this behavior is unspecified or non-deterministic or whatnot. They just basically said, don't call these instructions that cause unspecified behaviors. And this was a fine plan if you're going to prove a security, if you're going to prove a functional correctness property. If you're never going to call these opcodes, that's all great. But if you're trying to prove non-interference, then, as you guys probably remember from 2 weeks ago, you really need full determinism. So non-determinism is really bad for non-interference. And this is a case where the model hid non-determinism away because they thought, well, we don't actually need non-determinism exposed. It's fine to hide it by having this sort of undefined behavior, which in some ways is non-determinism. But it's easy to look at this model and miss the subtle implication that if you have this overly simplified model of the hardware, it's not good for proving a confidentiality theorem statement on top of it. So it's a tricky sort of implication to get right. So that's sort of on the qualified guarantee part of it. The other view of the world that the paper espouses or sort of argues might be why proofs are useful is maybe the structured exploration view. And this is sort of a pitch that says, well, the reason the proof is great is because it'll force you to very carefully understand your system. It's kind of like an eat your vegetables pitch. It basically says, well, you know, it's good for you. You should go through it. You'll be better for the exercise. Yeah, I think also in many ways it's true. It like really forces the developer to think precisely. And one way to sort of understand the structured exploration view of the world is actually Butler, if you remember, gave a lecture quite early in this class explaining what is the sort of steps of verifying a system. The steps that Butler sort of argues are, well, the first thing you do is you write down what is the state of your system. And then once you write down the state, you write down the specification, how that state evolves when you do various operations. And then afterwards, you write down your abstraction relation to describe how your actual code relates to this logical state. And then after you've done all these steps, 1, 2, and 3, then you do step 4, actually do the proof. And one sort of comment that Butler had, if you remember, is that there's really diminishing returns of going down this hierarchy. So much of the benefit in helping the developers build more reliable systems comes from sort of doing the writing down a state, the spec, maybe even the abstraction. And this is a structured exploration, I think, view of why proofs are good, is like doing the proof or the steps leading up to the proof really forces you to understand what it is that you're writing much better. And then you will realize that you were writing bad code or buggy code to begin with. So this is an important point, and sort of the value of the proof here really, it's almost like a final step. It like forces you to have done all the previous steps before correctly. It's kind of a bummer in the sense that the value in the structured exploration pitch is really getting out of sort of the earlier steps over here, and the proof is mostly there to keep you honest that you actually did them right. If you knew that you got down a good state and a good spec and a good abstraction, you wouldn't need to do the proof. And in some ways, like if you're doing the proof and you're finding lots of bugs, probably not the right time to do a proof. You should have really convinced yourself things were correct before. It'll probably be a very painful experience, for example, if you're trying to do the proof and you're hitting lots of bugs, because that means you're having to go back and change your state or your spec or abstraction over and over. It's kind of a weird artifact, this proof thing at the end. It's really this forcing function in some ways, if you're thinking about what is the effective way to get more reliable systems. So maybe one interesting thought experiment to keep in mind is like, where do various papers that we've read fall in this sort of value proposition almost? So maybe I'll sort of claim something, but I sort of think of, maybe in this left category where we have the qualified guarantees, I think we actually have systems like actually even Facebook's Infer. Those guys actually do try to, if you remember, they really go for like 0 security bugs. That's their goal. So I think they are indeed in some way really going for this qualified guarantee story, like the security bugs that they are set up to handle, they're gonna try to make sure there's none of them left. So they're really going for this value proposition. And other systems that really aim to have a very low level of abstraction underneath of them. So things like maybe the Iron Fleet paper, where they compile all the way down to assembly, or in some aspirational sense, the Everest project, also aiming to have a very strong coupled together stack that's rooted in fairly low level of assumptions. I think they really do want to have this strong qualified guarantee. And on the flip side, on the structured exploration side of the world, I think the Amazon paper is probably here, where they're using the proof, or actually not even the proof necessarily, maybe just some model checking, to really force the engineers to struggle with formalizing their spec and understand the problem better. And maybe other papers that we've read, like the verified paper about SDN controllers, is probably in this category. If you remember, they had all kinds of strange assumptions and so on, but like they really elucidate the problem space by going through that exercise. And maybe the I4 paper on distributed system invariants maybe falls in the structured exploration category as well. That makes sense? One interesting thing I was thinking about when I was sort of trying to figure out what does structured exploration mean, one interesting property is that when you're doing proofs, or at least in our research experience, sometimes we're doing a proof of a system, and then we realize that, oh, there's actually a bug in the low-level API that you're building on top of. But actually what's often going on is that you're doing a proof and you find this bug in the layer that you're building on top of, and you fix the bug and you keep going on your proof and the proof goes through. And I think what that says to me is that oftentimes the proof engineer or the developer actually has the proof right or correct in their head. And that's really sort of, they have a plan that's not formally or precisely tied to the platform on which they're building. Another maybe way to try to compare these is that in some ways, these structured exploration approaches are perhaps more manual oriented. They involve the developer trying to go through a bunch of steps and do like interactive cock proofs. Whereas I think some of these qualified guarantee approaches are much more automated, because their goal is not to get the developer to think clearly. It's really to guarantee something under a set of assumptions. So maybe not a perfect contrast, but something to think about in terms of what you might expect if you're contemplating doing a proof of a system. Make sense? Questions? All right. So the last thing that I wanted to mention from this paper is the side effects story that they have. Basically, they're sort of arguing that, well, maybe actually there are sometimes some downsides to doing a proof. And there's some things that we already covered. So like the significant effort is probably a real issue. If you're going to spend a bunch of time doing something, should it be a proof or should it be something else? Not actually clear. We also talked a little bit about having awkward code that you write as a result of verification. And another thing that we didn't touch on directly, but sort of shows up from the earlier paper on the empirical study, is that maybe the shim layer is more awkward. Somehow I switched to a highlighter. Maybe the shim layer is a little bit awkward if you're doing formal verification. So we saw a bunch of examples from that empirical case study of distributed systems paper where the shim layer had all kinds of bugs using a weird interface. And maybe if you're writing direct code in Go, or maybe even a Camel, maybe you wouldn't use such a rigid shim layer, and you wouldn't have quite the same set of mistakes in the shim layer. A little bit hard to say, but the other sort of 2 points that they made in the paper is that I wanted to get to. One that's probably most important is this sense of over-reliance on proven defenses. So this is the sort of maybe clearest example, is this example of rowhammer that I mentioned earlier, where like it's pretty common to have something like maybe a Java virtual machine or some kind of a JavaScript engine. And these guys actually provide isolation through memory safety. And they do so by carefully arranging things to be, maybe type safe, maybe every memory access is checked for bounds, and you're guaranteed that the code will not escape isolation. So the question is, if you have a proven JavaScript engine that's provably achieving memory safety, should you use other measures? So there's, commonly right now, if you look at a serious piece of software, there's probably lots of measures like address space layout randomization, or various canaries, or stack buffer overflow detection, or maybe defensive heap memory allocators, all kinds of stuff that watches for potential damage from memory corruption. So the question is, if you have a verified JavaScript engine, is it a good idea for you to stop using these measures just because you have a proof of correctness? And one way to think of it is that, well, I guess the concrete example I gave you guys was that maybe your memory is susceptible to rowhammer bit flips, and then, well, that's sort of undermines your whole proof. But sort of maybe more generally, I think it's important to keep in mind this idea of defense in depth for security. And maybe the way to understand why defense in depth is a good idea in the context of formal proofs is that defense in depth is not really there to prove the same properties that you've already proven. It's really sort of a strategy for mitigation if you have the wrong threat model. So it's all well and good that you have a verified JavaScript interpreter that provides memory safety, but there's a bunch of qualified assumptions in the sort of terminology of this paper, or something that has to go right in the threat model in order for that guarantee to hold. And probably you didn't get everything right. Maybe that's okay. Maybe you'll still have isolation. But on the off chance that you got the threat model wrong in some subtle way that also happens to undermine the real guarantee that you're trying to provide, having some defense in depth is going to help you in case you got the threat model wrong. So maybe one sort of big meta lesson from this paper is that you really should, watch out for defense in depth. It's a really important strategy for building secure systems, even if you've proven something to be correct. And one way to convince yourself of this is to think of it as the sort of insurance or mitigation for getting the wrong threat model, which is inevitably going to happen. The only question is it materially wrong or not? All right, so I think we're running out of time for discussion of this paper. Maybe the summary of this paper is really the positive way to internalize what this paper is talking about. It's really a story for what to expect from doing a proof of a real system and how to set things up, or like things to think about if you're planning to do a proof, to make sure you end up in a good place that you're happy with after you've done a proof. And it does seem like proofs help, but there's many nuances, and there are sort of things you should keep in mind. Don't fall for this defense in depth problem, for example, if you really want to have security at the end of the day. All right, so I should stop here, and if you guys need to run, feel free to run. We'll be around, so feel free to also stick around and ask questions if you have them. But otherwise, we'll see you guys on Thursday, where we'll have Shi Wang, professor from University of Washington. He'll tell us about some of his work on automated verification. See you guys then.